Hello, my name is Mauricio Atamura, and this is for COT 5405, and this is a suffix tree construction algorithm. So suffix trees. Suffix trees have paths that are created from all suffix substrings in a given string. So if we have a string that's 5 characters long, it, the tree would have paths that are the 5 characters, and then the last four, the last three, the last two, and the last one character. And we want to construct this tree in big O n or big O n log n time. We're going to assume that the alphabet set size is constant. So here are some examples of suffix trees. The first one here on the left is a suffix trie, where each edge is a character that represents a path that you can take. This type of trie is good for traversing the tree, but as you can see, it uses more nodes and uses more space. And then the middle tree is an implicit suffix tree, um, where the edges can have more than one character that denotes a path. And then on the right, we have what's called what could be called as a true suffix tree, where there's a $ symbol at the end of the string. And this is usually if one of the suffixes of the string is a prefix of another suffix, then we need the $ um, to distinguish. So a suffix tree construction algorithm. The algorithm I'll be talking about is Yukonin's algorithm, where it creates an implicit suffix tree. So to make t sub I plus 1, we have to build upon the implicit suffix tree that already exists of t of I. So we first have to construct t sub 1, which is the first tree, which has just two nodes, the root and the first character. And then after that, there are n phases, one for each character in the string. So a string of n characters, there's going to be n phases. And then in each phase, there's going to be and each I plus 1 phase is further divided into I plus 1 extensions, one for each of the I plus 1 suffixes in the string. So an extension I plus 1 of phase I plus 1, we put the string from I plus 1 to I plus 1 into the tree. So this is just one character which may not be in the tree. If the character is seen for the first time so far, we just add it as a new leaf edge with the label of S I plus 1. So this picture below is a pseudocode of this algorithm, where we first construct the tree t sub 1, and then after that we have two for loops within each other, going from one to the string length minus 1, as well as from for j from 1 to I plus 1 of that phase. We do, and then inside each phase we have to do the extension, what we call it the extension, where we find the end of the path from the root that we're looking at. So j to I in the current tree, and then we can extend that path by adding the character that we're moving up by 1, if it's not already there. If it's already there, then we don't have to do anything. And then this is a visual representation of a suffix tree construction using that algorithm. So we start with just a root node, and so for t sub 1, we would look at the first character, which in this case would be a, and just create a node with an edge a. And then when we see AB, we take this edge and extend it. So we add B next to A here. And then we have to create another path for B because a suffix substring of AB is B by itself. So then next we have ABB. So for this edge up here, we could just extend it to be ABB. And then for this edge down here, we can also extend it to be BB. And then here we have ABBA, so we can extend this top edge. And since we have ABBA, we have BBA as a substring and then BA as a substring. So we have to split this BB edge up so it can branch off to these two. And then for this image up here, we have ABBA, but this last A is also a substring. So we can split this apart if we wanted to. So so in the next picture, we split A because the next symbol we have is the dollar sign. So we could just have a dollar sign as the last one, and then as a suffix substring. And then we have a BBA dollar sign as well. And then this bottom subtree, we add dollar signs to the ends of those as they end with dollar signs in their substrings. And then for the whole thing altogether, the dollar sign by itself could be a substring. So we add the dollar sign as a edge to the root. So for the extensions, there are 3 rules that are followed. Where rule 1 is if the path from the root labeled J to I ends at a leaf edge. So if the path that we're looking at ends at a leaf edge, that means that the last character is the leaf edge. Then the character that comes right after it is just added to the end of the edge. So in the previous example, how A turns into AB, we just added B to that edge because it's a leaf edge, so we could just add it on top of next to it. And then rule 2, if the path from the root labeled J to I ends at a non-leaf edge, that means there's more characters after the string at I on the path, and the next character is not S of I plus 1, then a new leaf edge with label S I plus 1 and number J is created starting from character S I plus 1. And then a new internal node will also be created if S of 1 to I ends inside or in between a non-leaf edge. So how we split up the nodes before, creating the two children by cutting an edge, is what this is talking about. And then rule 3 is that if a path from the root labeled s of j to I ends at a non-leaf edge, so again, there are more characters after s of I on the path, and the next character, which is s of I plus 1, is already in the tree, then we don't have to do anything. So how the algorithm is described so far runs in big O n cubed time, but there are tricks to speed it up to linear time. So there's this thing called a suffix link, which is a pointer from v to s of v. So for an internal node v with a path label, let's say it's x a, where x denotes a single character and a denotes a possibly empty substring. So if we have, so it could be a x of x and then nothing, or x and then like a, or x of b, b, and then or x of bc or something like that. So it's some substring after x. So if there is another node after s of v with a path label a, then we can create a pointer from v to s of v, and this is called the suffix link. So in this example, in this image right here, we can see that the tree, the suffix tree is for banana, the word, and these green arrows are the suffix links. So we could take this arrow where it goes to A and then goes back, because here it's looking at a $, and the next suffix, like from the next link for it would just be $. So from a $, you chop off the a and then it just turns into $. And then for this node, it would be NA, where NA is the substring. So if we just chop off the N, we're left with just A. So we go to this node where it's A. And then for this one, it's NA, ANA, where if we chop off the A, it's NA. So we go to this node where it's just NA. And then another speed up technique is to skip /count. So when you're walking down from a node, let's say S of V, to a leaf, instead of matching path character by character as we travel, so matching each character by character in the path, instead of doing that, we can skip directly to the node, to the next node, if the number of characters on the edge is less than the number of characters we need to travel. And then if the number of characters on the edge is more than the number of characters we need to travel, we can directly skip to the next character on that edge. Thus, we can reduce the work to be equal to the number of nodes in the path instead of the length of the suffix of the string that we're looking at on that path. And then another technique is once a leaf, always a leaf, where once a leaf is created and labeled, let's say J, for a suffix starting at position J in the string, then this leaf will always be a leaf in successive phases and extensions. So once a leaf is labeled as J, extension rule 1 will always apply to extension J in all successive phases. Other areas that are related to suffix trees are suffix array constructions, where here in this left image, we can see that this is a suffix tree, like visually, not a suffix tree, but like the suffix is shown here. And then here's the suffix array construction, where it alphabetizes them and then does it by length. When it keeps the array number attached to them. So the suffix array for banana would be this. There's also the longest common prefix, LCP array construction, where if we take banana again and find the suffix array of it, it compares the current array index to the next one, so A and ANA, and it sees what's the longest common prefix. So they both have A, and then they don't have N, like this one has N, but this doesn't have anything after it, so they just both start with A, so it's just one. And then NAA, and ANA, and ANANA have the first three characters in common, so 3, and then it just keeps doing that. So this is a related area to suffix trees. And an application for suffix trees would be an exact string matching, where we want to know all OCC starting positions of a target pattern string. So if we create our suffix tree in big O n log time, big O n time, we can traverse the subtree with the root of the last character in that target pattern string. So here, if our target pattern string is AGA and our string is CAGAGA, we could go AGA, and then here we could traverse the subtree with this root, and its size is going to be big O OCC. Another application of suffix trees is for a problem of longest repeating substring, where we want to know the longest repeating substring in a string. So first we make our suffix tree in big O n time, and then we have to traverse the tree to find the deepest internal node, which should take big O n time. So all of these nodes here that are not filled in are leaf nodes. That means they have no children. Where an internal node has at least 2 children. So starting from the root, we find that this is the deepest internal node, where it's 2. And this is also an internal node, but it's not the deepest because it only has a level of 1. So this one that's 2, we could see that the path is AGA, which is indeed the longest repeating substring. These are my references where I got my pictures and explanations for most of the stuff. And yeah, that's about it.